Okay, here we go. We're going to learn about nomenclature for a variety of different bonds. We're going to start off with the ionic bonds, then we'll look at covalent, and then some other special cases like acidic solutions. So to start off with nomenclature, it's important to realize that this system was developed for the whole world, so it's the international system. So this consortium, if you will, of different scientists got together and set certain rules within chemistry, among other things, I believe. They're most famous for their naming system. So that's where you get the International Union of Pure and Applied Chemistry. You'll typically hear this IUPAC name get tossed around. And that's really what they're referring to is IUPAC as the nomenclature system. And we end up having to use this because for different compounds we could end up with very similar formulas, and if we weren't careful with how we approach the name, we could get the same name. So what we want to do is make sure that for a new compound that it has a new name that is distinct from everything else before it. Okay? So one of the things that we ended with in our last lecture is that we had different types of bonds, and we really addressed pretty much ionic bond and covalent bond as the two classes. So what we're going to do in chapter 6 is learn how to name these compounds. So with an ionic bond, you're looking at a metal and a non-metal. What you may have not seen yet is that your metal will typically have your positive charge, also known as a cation, and your non-metal comes out as a negative charge, and you've got your anion. So hopefully you remember that when we talked about our charges. With ionic bonds, because we have this very regular positive-negative system, we get a lot of repetition within it. So an example that's shown there is in the lower right-hand corner is your very regular crystal structure. So trying to decide what's the molecule, if you will, within that becomes difficult. So instead of looking at it as a molecule, we'll typically refer to it as the formula unit, which is your smallest repeating unit. Okay, so that's what's going to happen with your ionic bonds. So whenever we're trying to discuss them, you have to realize that a sample is going to have a whole bunch of these in very regular alternating fashion, but we're really only thinking about that simplest combination. There are two classes of ionic compounds. You get your binary ionic and your ternary ionic. You can take advantage of the names to try and identify some information about them. The bi meaning two. So we're looking at two airy ionic compounds, so two atoms. Okay. This is actually extended a little bit further, and we don't look at it as just two atoms. We tweak that definition a little bit into element types. Okay, so what do I mean by that? Well, we could look at something like sodium chloride, okay, NaCl. That only has two elements. We could also go through and look at, say, another ionic compound. We could look at iron oxide. So iron and then the oxide, and we could look at something along these lines. Well, we have differing numbers in there, but it's still considered binary ionic because you have only the two elements. Okay, so it's not the number of elements in it, or the number of atoms in it, it's the number of elements in it. Okay, so just kind of be aware of that. Ternary ionic, ter for our root, allegedly, for 3. Your ternary are a little bit more complex. In this case, we are looking at a metal bonding with, so any type of metal, and again, in any kind of numbering amount, with non-metals that are now making up, another non-metal. Okay, making up a composition of a new compound or a new ionic form. So an example there would be something along the lines of, let's say, potassium sulfate. So your potassium is your metal. We need 2 of those, so that's what that 2 is for. We'll address that as we deal with this. And then our nonmetal is the complex ion sulfate. This is effectively a new unit, or one unit within it. Okay, so that doesn't get split apart into separate sections. That species is really what we're looking at when we're looking for ternary ionic. That species is more commonly referred to as a polyatomic ion. Poly meaning many atoms. Okay, so just kind of be aware of these developments with it. Each of these have slightly different rules. I would probably go as far to say as the binary ionic is probably going to be the most difficult to go through and name. The ternary ionic really just requires memorization for those polyatomic ions, but you follow the same rules as the binary ionic. Okay, so let's go ahead and get started with how we can go through and start to name these. So first we should come up with a naming system for the individual atoms, or technically in the case of an ionic bond, the ions that make up these bonds or these molecules. So our cations are almost always being referred to as the metals. Why should we see the metals as our cations, or our positively charged species? Well, if you go back to the periodic table that we put up in previous slides, where I said what are the charges, or I provided charges for different species, you'll notice that all of the nonmetals were negatively charged and all the metals were positively charged. So based on kind of a general rule, your cations are typically going to be metals. Why would your cations be metals? It's easier, why would your metals be cations? It's easier for them to lose electrons to look like your noble gas than it is for them to gain electrons, and that's where they fall in the periodic table. Okay, so just kind of remember that vaguely. Naming cations is pretty simple. What we're going to do is specify the parent name of that element or the symbol, and then we'll follow it up with ion. So the 2 examples given here would be Na+, which is sodium ion, or magnesium +2, or sorry, Mg +2, which is named as magnesium ion. Okay, so what we're trying to do is specify as much information as we can. So when we look at sodium ion, we provide our symbol, and then that ion necessarily implies that it is going to be a charged species. Your charge, well, let's make this a little more general. Okay, so we've got our symbol. Our charge is going to get written in the upper right hand corner, okay, for every symbol that you're going to deal with. So when we look at sodium ion, we would piece that together by saying our sodium gives us the Na. The ion part of the name is what's specifying our plus symbol. Well, just by specifying ion, how do we know it's +1? Okay, why would we know that? Well, there were the 2 ways we could look at it. We could have memorized all of those charges. Remember I said those charges were important. This is one of the reasons why they're important. Or you could go back to their electron configurations and derive what its charge would be. There are some ions that have the exact same charge every single time. They never change. Sodium and magnesium happen to be those, which means whenever we specify that ion, we are aware of exactly what it means. When we look at magnesium ion, again, we could evaluate our name, magnesium. Our symbol is Mg. And the ion for magnesium would be a +2. We would know it's +2 based on where it showed up on the periodic table. Okay, it's in that second column of your periodic table, which means it would lose 2 electrons. If it loses the 2 electrons, it becomes +2. Okay. Another notational thing I'll point out here, more important with the magnesium. If you have a charge that's greater or less than 1, so if we have a +2, +3, +4, or -2, -3, -4, there's a couple different ways we can specify that charge. What you can see here is exactly how the textbook would reference it, okay, for our magnesium. They do the number first, followed by the charge. It's a notational thing. You'll notice if you look at the example down below with the copper ion, the bottom one was a version that I wrote, or an example that I wrote. The top one, our magnesium, is something the textbook put together. So it's just how people were trained to write out the charges. I personally am a sign, so plus or minus, and then magnitude writer. I will accept both answers in a short answer explanation for what the charges are. So it's not that big of a deal. Just realize you will see them both. So let me write that out again. Magnesium ion can be written out as magnesium plus 2 or magnesium 2 plus. They both mean the same thing. It just comes from what people prefer to see. Okay? So those would be your easy examples, if you will. You've got standard ions. They're always going to be that charge when they're an ion. Okay? So as you could very clearly see next, are there exceptions? Well, yeah, of course there have got to be kind of exceptions to this. And it's not really so much as an exception as in we have to refine our rule. If we move to the ions now shown below, if we try to name these based on the information we started with, we could call that first one copper, because Cu is copper, and then, sorry, let's go ahead and color code. We could call that copper, and we could follow that up with the word ion. Oh yeah, because it's an ion, it's charged. Okay, well what if we did the other one? Well, we could write that one as copper, and then ion. Woohoo, we get the exact same name for two ions. Is that a problem? Kind of yes and no. It wouldn't be a problem if the chemistry was identical for both of these ions. Is the chemistry the same? Okay, well, what dictates man, I can't say that word. What determines the chemistry for an individual atom? Okay, well, the atom chemistry is dependent on the electron configuration. So what you should be able to go through and do is determine the electron configuration. I unfortunately forgot to bring a periodic table with me, so give me a second. Okay, in theory I'm back here. We could look at our periodic table to determine the electron configuration. If you look, copper is, or has the atomic number of 29, so we could write out our symbol. We're looking at, atomic number down below, 29. We could take a stab at the mass number, though it's not that big of a deal, 63. If we were going to do our electron configuration, it's a lot of electrons to account for, so we can do some cheating. In this case, it's going to be argon, and then we're looking at 4s2, 3d, where are we? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. Okay, well, if I move a single electron away, that's going to give us a different electron configuration. And here I'm definitely going to make an idiot of myself because I don't remember which electron we remove. I believe it's going to be our 4s. So if we made it our first one, our copper plus 1, so we put our plus 1, we would remove an electron and we'd have 4s1. What if we made it copper plus 2? Well, now when we look at our electron configuration, it becomes 3d9. Well, is that a problem? Well, you tell me. Are we going to see a different interaction when that atom butts up against something else? In our copper plus 2, we're seeing the d orbitals interact with another atom. In our copper plus 1, we're seeing the s orbital. Different orbitals, different interactions, which means we have to give them different names. So what we're going to have to do is refine the nomenclature system that we've been working with. So instead of just calling it copper ion, we're now going to add an extra layer of information. For our first ion, that's going to become copper 1 ion. And we're going to dictate that with the Roman numeral 1 put in parentheses. For the next one, we will call it copper, any guesses? 2 ion because it's a +2 charge. Okay? So we just want to add that extra information when we go through and put our names together. You will have to come back to determining what these charges are depending on what they're bonding with, and we will see that when we deal with the formulas. Okay? So just make sure you remember that when you're naming your cations, if it's a cation where you are required or are expected to know the charge, then you don't need to specify the charge. If it is a metal where the charge is variable, which means pretty much any transition metal, and there's a couple exceptions to that, but any transition metal, you need to specify the charge on because that charge is variable. Okay, so we could have different versions. So make sure you keep that in mind when we put all this together. That system that we just addressed is looking at what's known allegedly as the stock system. There is another version out there. From what I've seen in my experience, it's really only used by very old chemists. Okay? And in that case, they end up using these Latin root systems, which I won't ever test you on because I can't remember it to save my life. Okay? But you might see these kind of terms float around with it. So another name we could go through to identify this is we use our Latin root. So for copper, it's maybe CUPP, I believe. No, we have to add at least an R. I think I'm spelling that wrong. I think it's only one P. I don't know. That's why I said I didn't like it anyway. The lower charge will change the suffix to an us ending. So for our copper +1, it's a lower charge than our copper +2, and we get cuprous. For our higher charge, it becomes, I think there's 2 P's. Nope, 2 P's looks pretty wrong. We'll call it cupric. And we'll still include the ion, so it would be cuprous ion and cupric ion. Just want to make sure you're aware of that. You might see that pop up in the homework. You might see it pop up in the textbook or in future classes. Again, it's kind of an age thing. Most younger chemists that I've talked to tend to not use this Latin system, so you could very well now spend the rest of your career and not have to worry about hearing this cuprous and cupric or this us and ic ending thing show up. Okay, it does show up every so often though, so be aware of that. Next part would be to look at the partner for your ionic compounds, and we'd be looking at anions. So again, we're going to name it based on the monoatomic, or sorry, a single atom of it. This is typically going to apply to our nonmetals. Why should it apply to the nonmetals? Well, go back and take a look at your electron configurations. Your nonmetals start much closer to your noble gases or your inert gases, so to make the electron configuration look the same, it's a lot easier for your nonmetals to take electrons and become negatively charged. So if we gain electrons, we become anions or negatively charged species. Okay? So just kind of be aware of that. Next part, when we go through to do the naming, is we want to separate these away from the cations because we can't possibly use the same name because that would make way too much sense. So instead of referring to these as, say, bromine ion or oxygen ion, we're going to tweak the name a little bit. And the reasoning actually makes a little bit sense when we put it all together. So what we're going to start off with is we'll take the root name from our element, and we'll change the suffix to an IDE ending. Okay? So they've given some examples, in fact they've given you a lot of examples down below. So if we go ahead and start with that first one, that element is bromine. Okay? Well, the root in that, and it's always going to kind of come up to different opinions, I would say is brome. So we would start with the brome followed by our ending of ide. So it becomes bromide. What happens in the case of iodine? Well, in the case of iodine, we look again at our root. Our root is the iode. Now follow with our ending. the IDE to make it iodide. So if I want to talk about the element or an atom of iodine, I have to say iodine with the Ne. Okay? If I wanted to talk about the charged atom of iodine, so I minus, I would now say iodide. It's a very subtle difference, and in class you may or may not have actually heard me already say multiple times and kind of backstep what I said because we hadn't talked about this yet. Okay? So that IDE ending is implying the charged or the negatively charged species. So a couple other common ones that we can look at just because it doesn't always look nice. Could take a look at oxygen. Okay, so what's the root in that? Well, you could come up with all sorts of different opinions, but if you take a look at what the answer is, your root ends up just being the ox. Okay, why? I don't have an answer for you, unfortunately. When it comes to nomenclature, there are rules to follow. You follow the rules and you're fine. You don't follow the rules and you're wrong. Okay, so just kind of be aware that these are going to be your most common ions showing up. Apply them appropriately. Okay? One of the things that we're not going to have to worry about when we go through and do this is we never have to specify the charge with these. Why not? Well, all of these ions are singly charged. They only have this charge when in an ionic compound. So there's another big caveat there. I said they always have the same charge when in an ionic compound. They must be bound to a metal. Okay? So remember that when we process these, that's how you're going to go through and evaluate. With our anions, we don't have to worry about the charge because they're always going to have the same charge. So less work on our part. I do just kind of want to throw in one more example here, just to kind of make it fun. What if I was looking at carbon -4? Okay, how would I name that one? So I already stated what we're looking at. We've got carbon. Okay, we now want to change that so that we can actually represent the negatively charged ion. The root in this case is the carb. We'll change our ending to the IDE, and we now have carbide. You may have actually even heard of this before. Was it titanium carbide? I don't know, there's some famous carbide compound that is a strong steel. Okay, and that's where it's coming from. That's why we call it carbide, is that carbon is being bound to a metal. Okay? So those, or that hopefully now sets you up with kind of the basics of the single ions. So now what we want to do is go ahead and make a compound. So in the process of making a compound, we're going to have to take at least one cation and at least one anion and bring them together to make our ionic bond. Okay? So in this case, I've got it kind of broken up into these individual sections. So C for cation, which I'm going to try and keep consistent in blue, and A for anion, which I'll try and keep consistent in red. Okay? So our cation rule, when we were going to name it on its own, is we would just go through and name the metal itself, or whatever that element was, followed by the word ion. For our anion, we change the suffix to the IDE ending. What happens when we bring them together? Well, when we bring them together, the metal is no longer an ion because it's now matched up, or not a free ion, because it's matched up with that negative charge of the anion. So we'll drop the ion part of the name. What happens with the anion? We've already adjusted its name. We don't have to touch it. Okay? So we can kind of simplify this. So you've probably heard of some simple compounds already. What if we looked at, say, this compound? Well, when we put these two together, remember it's a metal and a non-metal. So we're looking at a cation and an anion. When we bring them together, we would name our metal. Okay, so our metal in this case is sodium. Because it's in a bond now with that non-metal, our anion, we won't use the ion word. And the next atom is our chlorine, except it's now in a bond with a metal. So what we will do is change the suffix of our -ine to now become, oh shoot, running out of colors. Let's call it chloride. So the name of the compound, sodium chloride. Probably already heard that one now a couple different times. So let's try a different one. Let's try this guy. Whoops, sorry, that was a bit sloppy. Let me try that again. Let's do K2O. Okay. So one of the things that yeah, let's just go ahead and name this first. What's the K stand for? Hopefully you remember that that is potassium. Our red one, O stands for oxygen. And if you remember with that name, we change that now to oxide. Oh man. So while I'm rewriting that, this brings up another interesting kind of question that we should consider. When we look at this name, it just says potassium oxide. Does it say anything about the number of atoms of potassium or the number of atoms of oxygen? No, it doesn't. Okay, is it something that we should include in this? Okay, and that brings in a new question. Well, it turns out not. We don't have to specify it in this case because the name solves it for us. Potassium, when it becomes an ion, always becomes what charge? It is always K+. Oxygen, when it becomes an ion, always becomes, with air quotes, O-2. Okay? So what's going on with that? Well, if we go back and look at that very last statement, does our formula carry a charge? Okay, well, all of the compounds that you're going to be asked to name are going to be in the same kind of condition. Where do we find the charge? Go to the upper right-hand corner. The upper right-hand corner of that molecule, or let's even do the atoms. We can circle the upper right-hand corner for all of those. Okay, what's the charge for our potassium ion? +1, because we see a plus charge there. What's our charge for our oxide? -2, because we see a -2 charge there. What's our charge for the potassium oxide? Well, I don't see anything written in there. What does that mean? Well, what that means is that the charge is 0. It's neutral. Okay, well, why is that important? Well, what we're saying is that if potassium always comes in as a +1 charge and oxygen always comes in as a -2 charge, when I make a compound out of them and I make the neutral compound, I have to make sure that those charges balance each other. Okay, and we will look at an equation that can kind of relate this in just a second here. So what we need to do is make sure that when we put it together, that we have 2 potassium ions to balance out the charge of a single oxygen atom or an oxygen ion. Okay? So we just kind of have to watch for that, be careful, be aware of it. Okay? So the two, or the examples that we just looked at here, had a metal and a non-metal that always have the same charge. Okay, well, what happens if we switch to something else? Okay, well, you should already have a guess of a metal that doesn't have the same charge because we just looked at an example. Let's look at copper, or I mean Cu. Okay, what's the name for that Cu? Yeah, I know, I just told you. It's copper. Okay, well, we drop the ion portion of it and we could say copper oxide. But remember, when we talked about naming cations, okay, so our metals in an ionic bond, if we don't know the charge, we must specify it. Copper is one of those transition metals. We have to specify the charge. in some way or another. We can use Roman numerals, or we can go through and use that Latin root system, the us, ic thing. Okay? So how do we know what the charge is? So what we're going to try and do is break this out and say this is copper. Okay, should it be positive or negative? Well, our overall charge is 0. We know the oxygen is a -2. To balance that, the copper needs to be a positive charge, right? Okay, so we could look at it that way. The other way is copper's a metal. What charge do metals take? Positive. There we go. So it needs to be plus. But how big should that plus charge be? +1, +2, +3, +50 billion. Okay, we need to come up with some number for that. So at this point, what we could say is that is copper plus X, some unknown charge. And what we can go through and do is pull some information from our formula. We know we have one copper atom, right? We do not know its charge. So copper atom times its plus X. And if we add that to the one oxygen atom we have times its charge, that's an oxygen. I don't know how to make that symbol look like an oxygen. That has to equal our overall charge on our molecule. Well, what did we say the overall charge was in the case of copper oxide? Yeah, you're right, it's 0. Okay, we specified that right here. There's nothing written there, which means it must be 0. Okay, well, 1 times -2 gives us -2. So let's go ahead and just kind of, well, sure, let's just erase all of that. 1 times positive x equals positive x, so we can just write x. Okay, can we solve for what x equals? Should be able to. We can add 2 to both sides and we get that x is equal to 2. Now what do? We substitute back in our original thing that that metal ion is copper plus 2. How do we specify that in our name? Well, go back to how we name cations. We can use our Roman numerals. It becomes copper 2 oxide. Okay? So it takes a little bit of algebra, simple mathematics to play around with to try and figure out, in some cases, what the charges are on your metals. Okay, it's going to require a little bit of math to play around with that and get that set up. It takes a little bit of practice, and we'll formalize that equation here in just a little bit. Okay, so we now have the basics for how we put this together. Okay, so one of the things that's going to be extremely helpful to memorize is your ions. Okay, so what I would highly recommend you do is you memorize those that don't have the slash running through them. The reason I cross some of those out is that they have multiple charges. Okay, so if you look at, say, tin, okay, it's got Sn plus 4 and Sn plus 2. With those two charges, you don't necessarily know without specifying what that charge is. So that information would have to get supplied to you. Okay? You should recognize most of those. Your group 1 always come out as a +1. Your group 2 always come out as a +2. Your group 13, which is a little bit weird because all we're really looking at is aluminum, but we got +3. Carbon is weird, which is why it's left blank. We don't have anything there. But then our nitrogen is easier to go 1, 2, 3 to our noble gas, -3, oxygen, anything underneath it, -2, and our halogens, -1. Okay, so a little bit of manipulation with our tables can help us process and get through some of the memorization without actually having to memorize it. There are 3 elements on here that I really think that you're just going to have to straight up memorize. I don't know that I will necessarily make you memorize them, but I know in other classes you do, so it's not a bad idea to start. Silver ion, cadmium ion, and zinc ion all have 1 charge, and only one charge. Zinc will always be +2, cadmium will always be +2, silver will always be +1. Okay, why is it helpful to know that? Because then when you write out a compound or an ionic bond with those elements, you don't have to specify their charges with Roman numerals. Okay, that information is removed from the name, so you don't have to stress about it. So that can make things a little bit easier as far as naming. Okay, so let's take a look at some practice again. Oh wow, I happened to pick the two examples that we already did. So for our first case, we'll go ahead and split it. We've got sodium, followed by our red for our chloride. Both sodium and chlorine are elements that we know the charge is for. We don't have to specify the charge. If we went ahead and looked at the next one, Cu is for copper. Br is for bromine. Whoops. So we can change that to bromide. So we change our ending. We don't have to specify the amount of bromines or bromides necessarily. What we do have to specify is the charge on copper. Remember, copper is not one that you've got memorized or that you should memorize, so you're going to have to specify what it is. So how do we know what that charge is? Okay, well, we just talked about it. Bromine is a -1 charge. Copper has to be a plus something, so plus X. We know we have 2 bromines, and we know that when we do this math of adding these two up, we need to get 0. Well, the result is that copper needs to be a 2 charge. So in our name, it becomes copper 2 bromide. Okay. Again, we haven't formalized that equation yet, but I'm pretty sure that shows up on our next slide. Okay. So what we've gone through here is formula to name. Okay. Nomenclature is all about being able to name things, which means you have to go both directions. So the other thing you're going to be responsible for is going from the name to the formula. Okay, so how would we go through and do that? We've got a couple examples. So magnesium has what symbol? Good, Mg. Oxygen has what symbol? O, good. We now need to make sure that we've balanced the charge. So typically what I would do is go back to the name and specify the charges. Well, magnesium has what charge? Yep, a +2. Oxygen has what charge? A -2. When we add those two together, what do we get? 0, which means we don't have to specify any numbers. We have exactly 1 magnesium to 1 oxygen. It's perfectly balanced. We don't have to stress about anything. That is our formula for magnesium oxide, MgO. Kind of cool. Okay, how about the next one? Okay, this one it's kind of a butthead one. I didn't realize I did such a difficult one right away, but hey, we'll deal with it. Our iron is what symbol? Fe. Sulfide gives us what symbol? S. Okay, so all those element symbols and names you need to know. What's the charge on iron 3? Hopefully you can figure that one out as being a +3 charge. Okay, we'll add that to the charge of our sulfide, and our sulfide is what charge? Go up to our table and we're looking at a -2. When we add these two together, we need to make sure that our overall charge comes out at 0, which brings up an interesting issue. If we now add these and assume the numbers are 1 and 1, well, 3 plus a -2 gives us +1. Huh. That doesn't work. Okay? So what you would now need to do is find the common multiple of these two, or the smallest common multiple. You may see or hear a crossover rule. I'm not a big fan of that because there are exceptions to that, and I will test you on those kind of exceptions. What they're trying to get you to do with your crossover rule is that in a lot of cases, your common multiplier between these is going to be putting the number of the atom as the charge of the other one. So if I take 2 iron plus 3s, I now have a +6 charge. If I take 3 minus 2s, I now, whoops, I can do math. I have a -6 charge. The overall equals 0. I now have my correct formula. I would need to translate those numbers in. We'd get iron 2. Come on now, iron 2. And we would get sulfur or sulfide 3. Okay, that one's a bit more advanced, and by a bit I mean a lot more advanced. Okay, so kind of watch out for that. You have to make sure your charge is balanced in the overall name. So be aware when you go through and process those. So let's go ahead and formalize that whole equation thing that we were talking about. So everything that we're working with, and we've talked about this multiple times, we strive for neutrality, lowest energy. We're trying to neutralize these charges. When we look at composing a compound, we would assume that that compound, at least at this level, is going to come out neutral. So we need to make sure that when we put it together, we neutralize those charges and get our appropriate formula put together. Okay? To do that, what we're doing is setting up the equation, which is shown in a slightly different format that I've been discussing. This sequence of equations here. We'll take the number of our positively charged species, or our number of our cations. We will add that or multiply that by the charge on our cation. We can then add that with the number of our anion times the charge of our anion, and those two in combination will give us the overall charge on the molecule. How I've been writing it as we've been solving these, just to make sure you can see a slightly different format, the number of our cation times the charge, times our charge of our cation, you can see why I did it on multiple lines, plus the number of our anion times the charge on the anion has to equal our overall charge. Okay? As far as you guys are concerned at this stage in the game, your overall charge should equal, any guesses? 0. Okay? So let's reiterate the examples that you've already seen. So when we looked at CuBr2, whoops, I can spell copper. We had copper and then bromide. With that, we have to make sure that we specify the charge on our copper atom. We found out it was copper plus 2 by effectively using this equation up here and solved for the unknown. The unknown in that case was what's the charge on the copper atom. Okay? When we went through and did our iron sulfide, we start with our iron atom and our sulfide, and our unknown in this case would be the numbers for both of these. Okay, so with the bromide it was a little bit easier, okay, because with it being a -1 charge, it's really easy to find a multiplier that matches the other one. It's just going to be that same number across. When we look at the charge on something that, or two atoms that have different charges or non-1 charges, that becomes a little bit more difficult, and that again we can still use that same sequence of equations to kind of predict the lowest common multiplier, and we would get Fe2 sulfur 3, or S3. Okay, so we got a new example showing up at the bottom, aluminum oxide. So to start off with that, our symbol for aluminum, Al, our symbol for oxide is coming from our root for oxygen, of O. We now want to go through and specify our charges for each of these. Okay, well, oxygen, well, let's start with aluminum. We do not know the number of our cations, so we can put that as what I would specify as an X. The charge on an aluminum atom is +3. It's one you need to know. Plus the number of our oxygen atoms, again, we don't know it, times the charge on our oxygen atom, -2, has to equal now our overall charge. Since we didn't call this aluminum oxide ion, must be 0. Okay? We can now go through and try and put in different numbers for X and Y to make sure we get this 0 value. In a lot of cases, we can see that our common multiplier ends up being a swap of the other one. Okay, so the number 2 can apply to our X, and our number 3 can apply to our Y. Does not always work that way, but it works fairly commonly enough that we can, that you can probably get away with it in most cases. So we would get 3 for our Y, which we said was our number of oxygens, and we would get 2 for our aluminum, which is what we said was our number of aluminum atoms, or our X value. Okay? And if we want to accent that crossover a little bit more, could do it in this fashion. Okay? Takes a little bit of practice to get used to. One of the problems that I will put on the activity will not allow you to do the crossover. You'll find that there is a smaller common multiplier. Okay, so I want you to kind of be aware that we can run into exceptions to this common multiplier issue, this crossover rule. Okay? I would say, are there any questions, but you can't ask them. So we'll have to deal with that when we get to class. Those were our binary compounds. Now what happens is we can move into our ternary ionic compounds, which is really just a fancy way of saying polyatomic ion naming, which is also really just a fancy way of saying we have a couple nonmetals bound to some number of something else. Okay? Your polyatomic ions, so we'll address them on their own first before we look at larger compounds. They're almost always made up of nonmetals bound to nonmetals, okay, to generate an ion. So in previous cases, or in other cases, if we bound a nonmetal to a nonmetal, we might expect there to be no charge. In the case of a polyatomic ion, there is a charge. Okay, so remember that. Also, in most circumstances, we are looking at that nonmetal bound to some number of oxygen atoms. Okay, and oxygen, yeah, let's just kind of leave it at that. So if you go through and look at all of the possible polyatomic ions, you'll notice that we have a bunch of nonmetals, okay, in almost all of these cases. I said almost, chromium's definitely a metal. But in almost all of these cases, we have nonmetals being bound to oxygen atoms. Oxygen happens to be one of the more reactive species, which is why it tends to pair up with a lot of these complex ions. Okay, so you'll notice that there were some exceptions. For instance, we did have nitrogen show up once in one of the compounds, in cyanide, and we did have some metals with chromium showing up twice, with related compounds actually, and then also manganese. Okay, so what I've kind of laid out is the general rules behind it. How would you know the ratio that these atoms come together? Unfortunately, at this stage in the game, we are not teaching you how to put these structures together. We're expecting you to name them. So you have no predictive ability. So really what these are, go through and clear everything so you can see them all again. These are effectively new elements, if you will. Okay? So you have to memorize that when we're talking about sulfate ion in our lower right, that is the quote-unquote element of SO4 with a -2 charge. Okay, so these polyatomic ions are their own unit. You cannot separate, you cannot break them apart. Leave them together as one complete system. Okay? So treat them as you would the elements. You need to have them memorized. The more of these you have memorized, the better off you're going to be when you move into future chemistry classes. I starred, 7 polyatomic ions that I expect you to memorize. Okay? The other ones, I would hope that you spend some time and actually try and get those memorized and nailed down, but I'm not going to expect you to have those memorized. The ones that are starred in purple, you need to memorize. I will directly test you on those. You're going to need to have those at the back of your head. The main reason why we tell you to memorize things, because you can find this information. If you went out into the real world and you said, oh, what's the formula for hydroxide? Google's available. You look it up. Oh yeah, Google or hydroxide is OH minus. That's not the issue. The issue is that you use these commonly enough that you need to have that immediately available or recognized, okay? Which is something you'd have to do in the real world too, be it a nurse or an engineer or a doctor. Since almost everybody wants to be some kind of medicinal thing, let's think about a doctor. If you went into your doctor and said, I have all of these symptoms, and they said, okay, give me an hour, let me go check Google, you would probably flee their office as fast as freaking possible because you think they don't know what they're doing. Okay? There are books of all of that information. They know how to look through those books. The doctor that can go through and do that is still good. They just don't have all that information memorized. You already decided that they don't know what they're doing because they didn't memorize it. We're putting you under those exact same conditions that you're going to put your doctor under. Okay? So you need to go through and memorize these, otherwise we don't think you know what you're doing. Okay? So this test is going to be rough because you got a lot of big kind of concepts going along with it. Hopefully you guys will spend some time to get this memorized, and we'll work some problems that will hopefully build your memory a little bit better too. Okay? So your tips for your polyatomic ions, in case you couldn't guess, number 1 tip, memorize them. Okay? There are some other devices that I've heard other people go through and use and try and describe. None of them make sense to me, so you might go out onto the internet and see if you can find a better way to remember the arrangement of certain things. Okay? I talked about some patterns. I'm also going to address a few more patterns that we can look at. Again, I don't see how this is particularly helpful, but it's something that we can address. The more oxygens bound to a particular type of element, the suffix becomes an 8. Okay? So when we put sulfur, next to oxygen, we get our sulf as our root name followed by 8. Okay? We know it's the 8 ending because there's 4 oxygens and not, say, a lower number like 3. Okay? And if we shift it to less oxygen atoms, it becomes sulfite. Okay? Well, the first question that comes to mind when I say that is, how do you know there can't be 5 oxygens? Or 2 oxygens? Or 6 oxygens? I don't have an answer for that. And I don't think your textbook does either. They're just saying, oh, more oxygens equals 8. Okay? So it can kind of help if you remember bits and pieces of these formulas. Okay. So if we were going to take a look at these two compounds, we're looking at our nitrogen, so we're looking at and now we have to decide, is it the ate or the ite? Well, in this case, the most oxygens you can put around a nitrogen is 3, so the more oxygens, we now have nitrate for NO3 minus. For NO2 minus, you have nitrite. Okay? That's about all I can say on that. Another thing that you could go through and do is the observation for your chlorine and oxygen ions. For ClO4, notice that that is the most oxygens you can put on there, and we do have that 8 ending. Unfortunately, we also have ClO3, which has an 8 ending. And when we move to a lower amount, so this is good, we get the ites endings, but again we get 2 ites. So we now have to separate these compounds away from each other. We have to go above and beyond just the 8-ite difference. That difference is going to come in with the use of the word per for having a whole crap ton of oxygens versus the hypo, meaning we have as few as we can possibly put in. Okay? So as a random test on this, you think you can name BrO4 minus? Okay, bit more challenging to come up with that because that's not on the list I told you to memorize. You should still be able to figure it out though. Okay, so what we would do is compare it back to what we do know. Okay, well when we had ClO4 minus, the chlor, our suffix or our root for our element, was right in the middle. So we could put in our brome. We have 4 oxygens, which meant we had our 8 ending. Okay, and because there's 4 oxygens, we have a whole crap ton. We would call it per bromate. Okay. How do we know bromine would even pick up 4 oxygens? Well, where's bromine on the periodic table? Right underneath chlorine. Same properties. Okay. Another one, just to make it fun, let's take a look at IO minus. What's happening with this one? How would you name this? Well, your I gives you your iodo. Okay. We're actually going to have to delete that O. Because there's only 1 oxygen, we're looking at the ite ending, so it's iodite. Iodite, but there's only 1 oxygen, so we have to go even further and specify the hypo. So you get hypoiodite. Okay? So there is some sort of logic behind these, but not a whole lot. Okay? So, formula naming practice. Let's take a look at a few of these. I want to pick the first 2 you should be able to do pretty swiftly on your own, so I'm not going to look at those. Let's take a look at this guy here. To start off with, what's our cation, or our metal? Magnesium, which is Mg. Sulfate, you guys got that one memorized yet? I mean, that was only 30 seconds ago, right? You should be able to do that. Sulfate was SO4. Okay, remember, 1 huge big unit. Sorry, I should pick the right color. So SO4. Now what we've got to decide is how many of each of these showed up. Well, we'd have to go back to our charges. Magnesium has a +2 charge. Sulfate has a -2. If we add those 2 up, what do we get? 0. Yay! What does that mean? Our formula is set as is. There's our answer for magnesium sulfate, MgSO4. Okay. And if we want to get a little bit fancier, we could actually delete some of that space in between there. Okay, because we don't need that. Iron fluoride, I would expect you guys to be able to figure out on your own, might show up on that activity. So let's take a look at the cobalt chlorate, because that looks kind of crazy. So to start off with, cobalt symbol is CO. Our chlorate, anybody remember that one yet? ClO3. The charge on our cobalt was +3. Oops, got my color pattern wrong. Cobalt was our +3. Our chlorate was -1. For our charges to balance out, how many are we going to need for each of these? Hopefully you should see that we will need 3 chlorates. Okay, so we could just put a 3 after it, right? Well, what is that formula now say? Because that kind of looks like I'm saying it's cobalt, 1 chlorine, and 33 oxygens. And I didn't want to say that. I wanted to say there were 3 chlorates. To do that, I need to bring in my parentheses. Now the 3 refers to whatever's directly in front of it. Directly in front of it is the parentheses. So now everything in those parentheses needs to be multiplied by 3. Okay? So, oh man, more of these. Okay, let's take a look at one more as an example before we get through the rest of these, because this is already running kind of long. Last one down here, Cr is chromium. N is nitrogen. Because it's an ionic compound, this becomes nitride. So we get chromium nitride. Is chromium 1 you know the charge of? Nope. So we're going to have to specify it. You may or may not be able to figure out exactly what it is by looking at that formula. So what we can go through and do is say there are 3 chromium atoms times an unknown charge plus 2 nitrogen atoms. Nitrogen always carries a -3, which has to equal the overall charge of 0. We get 3x minus 6 equals 0. 3x equals 6. X equals 2. To specify that, we go back to our formula and say chromium 2 nitride. Okay. So again, it's going to take some practice. You can fully expect to see several of these show up in the activity. And why not? Let's go ahead and add a keyword here. There is going to be an online quiz that is going to be worth a substantial amount of points for the day. So on that quiz, I'm going to ask what the keyword was. Well, you ready? Your keyword, so this way you can go back through and look. Keyword is going to be red, as in R-E-D. Okay? You will need to type that in, because I'm not going to give it multiple choice. It'll be an online quiz, and you will have to type it in capital letters R-E-D. Okay, capital letters, so capitals will count. R-E-D. That's your magic keyword for your quiz. And now let's go ahead and erase that. Okay, so moving on. Covalent compounds. We're now actually getting into easier things, in my opinion. So we don't get the stacking that we would expect with ionic compounds. So instead of formula units, we actually get molecules. Okay. We also don't have a cation and anion as strictly as we would get in the ionic compounds, because we get equal sharing of electrons between the elements within a covalent compound. So it's going to be a little bit more difficult to figure out that order. So IUPAC stepped in and said, this is the order in which you arrange your atoms when you go through to put it together. Okay, I'm not positive on this, but you can go ahead and I can tell you already that's not true. Never mind. was going to say, I used to think it was based on electronegativity, but it doesn't look like it. So this is the order when you're told to provide a formula for a compound. Carbon always comes before phosphorus, comes before nitrogen, hydrogen, etc. Okay, so for instance, water. What was the formula for water? Well, it was H2O. Well, when you look at the formula for water, where's hydrogen? Comes before oxygen. Anybody know the formula for ammonia? NH3. Interestingly enough, hydrogen shows up after nitrogen. There's our explanation for our order. Okay? So our covalent compounds, nonmetals to nonmetals, and not charged. If they were charged, we'd have a polyatomic ion. So the first element in our formula will get its same name. The second element will get the extra suffix "ide," just like we did with our anionic compounds. Okay, so if we wanted to pick, actually, do I have an example here? Yep, here we go. Take a look at that first one. We've got carbon and oxygen, so we could call this carbon oxide, representing all of those things. What about the next one? Okay, well, we look at our orders again. Chlorine needs to come first, so we got chlorine oxide. Last one, carbon, sorry, I got a bit sloppy there, sulfide. Interesting dilemma here though. What's the problem? Well, that last formula incorporates a number. We got 2 sulfurs. Our name doesn't seem to specify that. And because we're now looking at things that don't have consistent charges, we've got a bit of a problem. How do we specify that we have multiple of that element? Okay, so we do that by bringing in Greek prefixes. Greek prefixes. So you'll always do the first element by itself, standard name. Second element ends with your "ide." And before each of those, you will specify the number of that atom using a prefix. Okay, so our example down below, we've got phosphorus. That's a really long one. Phosphorus, and then sulfur, so it becomes sulfide. Whoops, I did not leave myself enough space. Phosphorus sulfide. Before we actually specify these, we now need to drop in how many of each showed up. Well, for phosphorus, there were 4, so that gives us the Greek prefix tetra phosphorus. And then we had 3 sulfurs, that gives us trisulfide. So you now need to add some more things to memorize. You need to know your Greek prefixes, so that when you go through and name individual compounds, you know what these are referring to. I will simplify a little bit. I will say, as far as memorization goes for the exam, I will only test you on 1 through 5. Your homework will definitely push you above that. The problems that we do in class will definitely push you above that. But for the test, you only need to know mono, di, tri, tetra, and penta. Okay? I think we got another example. CO. Turns out it's a rule that we can't drop, or apparently we can't drop the mono. So that's not carbon oxide, but that is carbon monoxide. So we'd have to specify our monoxide. Okay? So you're not allowed to get rid of that mono for the second term, or the second element. The first element, if there's only one, we're fine to just leave it as that element name. We don't have to use the mono prefix. Okay? Oh my gosh, are we done yet? Binary acids. Binary acid is ultimately an aqueous solution of a compound containing hydrogen and a non-metal. Okay, so we've seen these before. We'll always begin with our hydrogen. So we've got our H, and then there's one extra piece of information there, is that it says AQ afterwards, specifying the phase. This is different from the compound shown there to the right, where it says HCl. What is HCl known as? HCl is hydrogen. Hello? Is hydrogen with an E chloride. Whereas this compound is known as hydrochloric acid. Different things. Okay? So to go through and do that, we start off our acid name specifying that we have that hydrogen with our hydro, and then we follow that with the next element, its root, with, and then we change our the suffix to the ic acid. So for the two shown below, we have hydrofluoric acid. And the next one we have hydrosulfuric acid. Okay? So that's how you're going to name your binary acids. Okay? Some of you may have heard of another acid name, sulfuric acid. Sulfuric acid is not hydrosulfuric acid. There are two different compounds. And we will see that in the next one. Your ternary oxyacids are now, again, aqueous solutions, starting again with our hydrogen, followed by a polyatomic ion. Okay, and this is where we get all these stupid extra rules. If your polyatomic ion ends in 8, then we change the ending to an ic acid. Okay, and we don't include the hydro. So our first compound becomes known as perchloric acid. Why the per? Because this is perchlorate. How about the next one? Okay, well, that complex ion is your chlorate ion, so our acid is chloric acid. Okay, what if your ending ends in ite? Well, then we've got, in that next case, this is our chlorite. So we have chlorous acid. Last one, this is hypochlorite, so it's known as hypochlorous acid. Okay, so it's just a question of changing the ending. We don't specify the hydrogen in this case because it's a ternary acid, not a binary acid. The name acid implies already a hydrogen. The hydro is only added to differentiate between binary versus ternary. Please say that's the last slide. Oh, shoot. Well, we're going to go ahead and call it there. The very last slide is just a quick test of some questions. We'll go ahead and do those in class because this video was already way too long. Thank you for your patience, and if you've now jumped to the end, I hope you found the key word. It's not at the end, it's somewhere further back along. So good luck finding that. Watch the whole video.